Good morning and welcome to this next lecture on sound and structural vibration. We are looking at oblique plane wave transmission through an unbounded flexible panel. So we have reached up to this point where the blocked pressure gives me the response. Okay. Now let us see on the transmitted side. So we are interested in C2 tilde. Should not forget that we are interested in C2 tilde. So the pressure on the transmitted side can be written as C2 tilde. The time, of course, minus K1 sine phi 1 z j, okay, minus j square root of K2 square minus K1 square sine square phi 1 into x. Okay, so for far field transmission this should be a real number, for far field transmission. So that's one condition. Okay, so what does that give me? Let's say that says if you compute sine of phi 1 has to be less than C1 by C2. I'd like to make a correction here. I'm using M everywhere, so this dash should not be there. Next, if I again use my Euler equation, okay, and say del P positive by del X is equal to minus rho 2 del V by del T, which is minus j omega rho 2 V tilde. Okay, then that means C2 tilde minus j K2 square root of 1 minus K1 sine phi 1 by K2 squared into e to the power of j omega t minus K1 sine phi 1 z. We are doing this at x equal to 0. Okay, that is equal to minus j omega rho 2 into the velocity e to the power of j omega t minus K1 sine phi 1 z. Okay, now this phasor part goes away. Okay, so that my C2 the tilde is equal to minus j omega rho 2 V tilde by minus j K2 square root of 1 minus K1 sine phi 1 squared by K2 squared, which is equal to rho 2 C2 V tilde by square root of 1 minus k1 sine phi 1 by k2 whole square. This is Z tilde fluid impedance 2V tilde. Okay, if you see our earlier here. Okay. Now, so we have found V tilde from blocked pressure. Okay, so C2, which is our interest. Again, let me remind you that this is the transmitted pressure amplitude, this is the velocity of sound in the right side medium. Okay, so C2 tilde is equal to Z tilde WF2 twice A tilde, I think I'm using, divided by Z tilde WF1 plus Z tilde WF2 plus Z tilde W panel. Okay. Now, we want the intensity transmission coefficient and then the power transmission coefficient. The intensity transmission coefficient. The intensity transmission coefficient tau is given by C2 tilde magnitude square by 2 rho 2 C2 divided by A1 tilde magnitude square by twice rho 1 C1. Okay, because the media are different, there is refraction. Okay, now once we bring in we want to get to the power transmission. Okay, power transmission. It means some area term has to come in. Okay, now that area term is going to be what? Okay, there is a slight difference in the beam width. Okay, so if I say this is my panel, this is my panel, let's say, and this is my wave vector, my wave vector. Okay, so these are the wave fronts. So this is the beam width here, but if the wave vector is in this direction, changed direction here, changes direction here, okay, then the normal is like this. So now this beam width is different, the beam width is different. Okay, so the beam width that is working on the half cell of a panel. Okay, this beam works on half cell of the panel, that beam works on half cell of this panel, so the widths are different. Okay, so that width has to be brought in to account for the power transmission. Okay, so far as intensity transmission it's okay, but once you talk of power you have to bring that beam width in. Okay, so if you bring that beam width into the picture, the width ratio happens to be cosine of phi 1 by cosine of phi 2. okay, which is square root of 1 minus sine square phi 1 by square root of 1 minus C2 sine phi 1 by C1 whole squared. Okay. So now we write the power transmission coefficient as this, given by, okay, let's call it tau p, given by 4 magnitude of z tilde WF2 square, okay, divided by magnitude of ZF1 plus Z fluid 2 tilde plus Z tilde panel squared into rho 1 C1 by rho 2 C2, and this beam width term 1 minus C2 sine phi 1 by C1 squared by 1 minus sine squared phi 1, both under the root. Okay. So this is the true picture when you have two different media. So we will not continue with this thought for from here onwards. So first thought is media are same. The media on both sides are same. That simplifies certain things immensely. Okay, so that the Z tilde F is twice Z tilde WF1 or twice Z tilde WF2. So we will use this notation. Okay. So what is now the power transmission coefficient? Z tilde WF magnitude squared by magnitude Z tilde WF plus Z tilde WP magnitude squared. Okay. If you put in all the terms now, okay, if you put in all the terms, what the impedances stand for, if we put the expression now comes out to be tau p, or tau is equal to twice rho 0 c sec phi, okay, whole squared divided by twice rho 0 c sec phi plus d over omega eta k fourth sine fourth phi squared plus omega m minus d by omega k fourth sine fourth phi squared. Okay. Now please remember this, that kb to the fourth is omega square m by d. The panel free wave number. Okay, so let's look at this picture once. So I have my acoustic wave number going this way straight up, and this is the panel free wave number. As I said, I use Kp and Kb interchangeably. We'll stick with Kb for now. So the panel free wave number goes like this. Okay. Now coincidence. Now the coincidence, what is coincidence now? It is the forced z wave number being equal to the free wave number of the panel. That is coincidence. It's like resonance. What I am forcing is equal to what is naturally liked by the system. So forced z wave number is k sine phi. So k sine phi must be equal to kb, okay, which is omega square m by d to the power 1/4. Okay. Now sine phi is a reducing factor. Sine phi is less than 1 always, so it will reduce. Okay. So that means what? K has to be greater than kb. K has to be greater than kb. Okay. So now there are two terms that you can control, the frequency and the angle. These are the two terms you can control so that the product is equal to kb. Okay. So if I am at a high frequency, suppose I am at a very high frequency, let me redraw this here. Let me redraw in this way. This is my wave number acoustic. So let's say this is my panel wave number. So this goes here. Okay. So I'm at a very high frequency. That means K is much bigger than, I'm here, much bigger than KB. KB and K. Okay. So I have a certain angle of phi which will give me equality. Okay. Then I have smaller and smaller angles of phi which will also give me equality with KB. Okay. If I can go to a higher frequency, then phi can be even smaller, so that K sine phi equal to KB. Because K is high and sine phi brings it down. Okay. So a smaller phi will be smaller sine phi, so that K times sine phi is equal to KB. That's at higher and higher frequencies. Okay. But if I now come down in frequency, okay, then my K is not so much bigger than KB, so my sine phi cannot be that small. okay, and in the limit when k is equal to kb, then phi has to be equal to pi by 2, okay, at which you can have coincidence, because sin pi by 2 is 1, then k is equal to kb. But if you now go below, that means k equal to kb, below this, which is basic coincidence frequency, okay. If you go below the basic coincidence frequency, which you should know, it is equal to c square m by d to the power half, okay. This is a basic panel fluid coincidence frequency. If we go below that, then there is no phi angle for which you will have coincidence, okay. So that should be remembered. So now the what did we do here, let's see. Okay, so if we now use these, let me rewrite actually, we have tau p or tau, intensity and power are same because angles have turned out to be same. So you have twice rho 0 c sec phi whole squared by twice rho 0 c sec phi plus d over omega eta k fourth sine fourth of phi. This is kz to the power fourth, you should remember, this is kz to the power fourth, okay, whole squared plus omega m minus d over omega, again k sine fourth phi whole squared, okay. So if we divide by omega m, what do we get? We get twice rho 0 c sec phi by omega m whole squared by twice rho 0 c by omega m sec phi plus d by omega square m, okay, eta k fourth sine fourth phi whole squared plus 1 minus d over omega square m k fourth sine 4 phi squared. Remember, d by omega square m is kb fourth, d by omega square m is kb fourth. So we have the ratio of the forced wave number and free wave number here, okay. So yeah, so I think I have written it like that again. So I have the numerator, I have the denominator, which is twice rho 0 c sec phi by omega m plus k by kb whole fourth eta sine 4 phi whole squared plus 1 minus k over kb whole fourth sine fourth phi whole squared. Okay. So based on your frequency, based on the frequency, because again we are saying that we have to equal k sine phi with kb. Okay, based on how high you are in frequency, you have a range of sine phi to match kb. Okay, but once k is equal to kb, that means your current frequency is the coincidence frequency. Okay, only phi equal to pi by 2 can match. Okay, so if we look at this equation, k sine phi is equal to omega square m by d whole to the power 1 by 4, right? Then, and we are talking of coincidence. We are talking of coincidence with angle phi. Okay, so we have coincidence frequency with angle phi divided by c. Okay, sine phi is equal to omega c0 square m by d to the power 1/4, or the coincidence frequency is now a function of the angle phi. M by d goes half, then c by sine phi square. Okay, so as sine phi goes down, okay, the coincidence frequency has to go up. Okay, as sine phi goes down, your coincidence frequency has to go up to give a match with the bending wave number. Okay, whereas if phi is 90 degrees, okay, then you are back to your original basic coincidence. Okay, which also means that if you are at such a frequency that k and kb are already equal, then no other sine phi will give you a match except phi equal to pi by 2. Okay, so phi equal to pi by 2 is the lowest frequency. Below, if you are below the basic coincidence omega c, if you are below this, then you cannot get coincidence, no coincidence. Okay, so now we will look at various regimes based on this formula over here. Okay, meanwhile the time is actually up, so I will close the lecture here and continue in the next class.